Good morning. My name is Svetlana Avramov-Zamanovich, and I come from the Department of Weapons, Robotics, and Controls Engineering at United States Naval Academy. My collaborators are Midshipman Kyle Jung and Reza Malak Madani from the Department of Mathematics. Before we go into our solution on numerical study of Paraxial wave equation, I would like to show you a couple of things. And those are the laser beams that propagate in maritime environment. To your left, you have a propagation in the atmospheric environment. And you have a beam that carries orbital angular momentum, topological charge of 1. And on your left, you have a beam that propagates in underwater environment where we have optical turbulence present due to the temperature changes in the environment. So refractive index changes significantly, and that is producing the changes in the intensity of the beams that propagate. At the Academy, we are interested in designing laser beams that give us advantage in constructing communication links in complex media. That is the overall arching goal. What we are considering is a transmitter. How can we generate beam? What are the technical constraints? What are the mathematical constraints? What properties of the beams we can use to strengthen its performance through the changing environment? How's the environment influencing the propagation in maritime areas, underwater, above the water, and so forth? And what do we do with the receiver? How do we record light intensities? How do we code the transited messages? So all of these questions all relate towards the fact that we have to know how does the beam propagate through the complex environment. We do experiments in the field. And you have in one of our field experiments on the Severn River, we propagate about a kilometer-long link, and we are observing how the beam changes, and we are measuring the environmental properties using scintillometers. The other experiments for the underwater, we perform in the laboratory, and we use heaters to change the temperature along the path of the beam. We use the spatially partially coherent light, and we use the light that carries orbital angular momentum as our structured light so far in our study. So the overall objective is, can we structure the light in such a way that it propagates successfully through the field of changing refractive index in space and time? For our study in COMSOL, we are solving Paraxial wave equation. We had chosen to do it with normalization of the lengths, and we also separate the real imaginary part. Through that process, we got a biharmonic PDE. Also, I would like to note that our work in this conference is actually threefold. We have a poster, and we submitted a paper and this presentation, each of which is focusing on solving Paraxial wave equation in COMSOL, and we are also using Garlican method for solving PDEs to compare the results. In a COMSOL setup, we had to set auxiliary variables because of the fourth order derivatives we have, and our COMSOL model is presented in this slide. What's important for COMSOL is always initial and boundary conditions. We decided to go for Dirichlet boundary conditions in our case, and initial conditions we set up from the theoretical solutions for unbound space propagation in the vacuum. So those are the derivatives that are necessary and solutions for the initial conditions that we had submitted to COMSOL solution. COMSOL simulation, in our case, we used MASH, which is concentric cylinders. We propagated through the cylindrical cavity. The radius is about 10 meters, which gives us almost like an approximation of unbound space. We used more coarse meshing towards the boundary, and also a finer mesh in the on-axis where the beam actually propagates. COMSOL requires us to provide 8 initial conditions to do our setup. It is not necessary that we provide auxiliary variable initial conditions from a mathematical point of view. So we decided to go two ways. We set up those initial conditions to 0, and we obtained the solution. And we actually calculated those initial conditions, provided them to COMSOL. There was no change in the solution of the beam intensity on axis for either case. Our results are presented on this slide. We have in red what COMSOL solutions gave us, and in black what is the theoretical solution. The discrepancy in the intensity is in both the location of where the peak intensity occurs and its magnitude, as well as a teeny tiny fluctuations of the intensities as the propagation length extends. The more detailed view of our solutions, because we do have the real and imaginary part of the intensity solved by COMSOL, we can clearly see some of the oscillations towards the higher propagation lengths, as well as the offset of the peaks and the contribution from actually both M real and M imaginary in our case. More striking are actually oscillations that we do see in the auxiliary variables that are the derivatives of these, and we can see the oscillations actually occurring even before the beam waist slightly, and then definitely extending more pronounced towards the higher propagation length. Our next steps in our work definitely are verifying the discrepancies between the exact solutions in Unbound and the COMSOL solutions. We would actually like to learn a little bit more about how COMSOL evaluates its convergence and see how that is influencing our solutions. The next step is definitely looking into the whole beam, not only on-axis propagation, because that is what actually is absolutely necessary for the communication links we would like to study, and the introduction to the COMSOL of the fluctuation in the refractive index in both space and time. Thank you for your attention.